Tonight, we're going to solve a murder. The largest mass murder in the history of complex animal life on this planet. The event that ended 165 million years of dinosaur dominance in a geological instant. The catastrophe that killed 3 out of every 4 species alive on Earth and reset the trajectory of life so completely that without it, you almost certainly would not exist. We know who did it. We found the weapon. We found the crime scene. We found the body, or rather 75% of the bodies, because that's how many species didn't survive. And we spent 50 years piecing together exactly how it happened, what the sequence of events was, what killed what, in what order, over what timescale, with what mechanisms. And the answer is more complicated, more violent, and more strange than almost anyone realizes. Because here is the thing most people don't know. The asteroid hit. That part is true. A rock roughly 12 kilometers across, wider than Mount Everest is tall, struck the Yucatan Peninsula in what is now Mexico at approximately 20 kilometers per second, 66 million years ago. That part is settled science. The evidence is overwhelming, and the crater is still there, buried under sediment and ocean, identifiable by geophysical surveys. But the asteroid alone may not have been enough. What killed the dinosaurs was not just an impact. It was a sequence of events, a cascade of catastrophes, each one feeding into the next, operating over timescales ranging from milliseconds to millions of years. It was heat pulses and acid rain and global darkness and starvation and ocean acidification and volcanic winter and a collapse of food chains so complete that almost nothing with a body mass greater than 25 kilograms survived anywhere on Earth. And this is the part that almost never gets told. There was already a catastrophe in progress when the asteroid hit. The dinosaurs were not thriving in paradise when the rock arrived. They were already under stress from the largest volcanic eruption in the history of the Cenozoic era. The asteroid hit a planet that was already wounded. Tonight, we're going to go through the full story, every stage, every mechanism, the timeline of destruction from the moment of impact through the years and decades and millennia of aftermath. The science that took 50 years to accumulate because each piece of evidence required new technology, new techniques, new ways of reading the geological record. By the end of tonight, you're going to understand not just that the dinosaurs died, but exactly how. And you're going to understand something about the fragility of the world you live in, because the mechanisms that killed the dinosaurs are not gone. They are the same mechanisms that shape life on this planet today. Before we get started, if you love exploring the depths of the past as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand what died and why, you first need to understand what the world looked like in the final days of the Cretaceous period. The geological epoch that ended 66 million years ago. The Earth of 66 million years ago was warmer than today. Significantly warmer. There were no polar ice caps. Sea levels were higher, perhaps 100 to 200 meters higher than today, because of the higher temperatures and the lack of large ice sheets. The continents were arranged differently than now. North America and South America were not connected. The Isthmus of Panama didn't exist yet. India was an island, still moving northward toward its eventual collision with Asia. Australia was further south. The Atlantic Ocean was narrower. The climate was warm and humid, with dense vegetation covering much of the planet's land surface. There were no grasses. Grasses would not evolve until the Eocene, millions of years in the future. The dominant plants were ferns, cycads, conifers, and flowering plants that had been diversifying rapidly for the previous 30 to 40 million years. The Cretaceous was the epoch when flowering plants first appeared and began their conquest of the terrestrial landscape. In this warm, lush world lived an extraordinary diversity of life. The seas were full. Ammonites and mosasaurs and plesiosaurs, and fish and marine reptiles of astonishing variety. The skies were full. Pterosaurs of multiple species, and birds, which had already diversified substantially from their theropod ancestors. The land was dominated, as it had been for 165 million years, by dinosaurs. The dinosaurs of the late Cretaceous were not the primitive creatures of early dinosaur evolution. They were the product of 165 million years of evolutionary refinement. Sophisticated, successful animals adapted to an enormous range of ecological niches. Triceratops and its ceratopsid relatives grazed in herds across western North America, their three-horned skulls used in display and combat. Hadrosaurs, the duck-billed dinosaurs, were among the most abundant large herbivores, some species forming enormous migratory herds. Ankylosaurs carried armored bodies and club-like tail weapons. Pachycephalosaurs used their thick domed skulls in headbutting contests. Titanosaur sauropods, enormous long-necked plant-eaters, still walked the southern continents. And the predators, tyrannosaurs, including the iconic Tyrannosaurus rex, were apex predators in North America and Asia, the largest terrestrial carnivores that had ever lived. Abelisaurids patrolled the southern continents. Dromaeosaurids, the raptors, hunted in smaller packages but were no less effective. The world of 66 million years ago was full, diverse, successful. The dominant group of large animals had been in place for 165 million years, longer than any other group of large vertebrates in the history of life. There was no reason to expect that anything would change. And yet, everything was about to change. In minutes. Part 2. The Weapon. What we know about the Chicxulub impact. The story of how we identified the weapon, the asteroid that ended the Cretaceous, is itself one of the great detective stories in the history of science. In 1980, a physicist named Luis Alvarez and his geologist son Walter published a paper in the journal Science that would eventually transform paleontology. They had been studying a thin layer of clay, only a centimeter thick, that appeared at the boundary between Cretaceous and Paleocene sediments at sites around the world. This thin layer marked, precisely, the moment in geological time when the dinosaurs and 3/4 of Earth's species disappeared from the fossil record. What Luis Alvarez noticed was that this clay layer was extraordinarily enriched in iridium, a rare metal in Earth's crust, but relatively more abundant in asteroids. The iridium enrichment was not just at one site. It was global, found in Cretaceous-Paleocene boundary sections on every continent and in ocean sediments from around the world. The global nature of the enrichment ruled out any local geological explanation. Something had deposited iridium simultaneously everywhere on Earth. The Alvarez hypothesis was initially controversial. Many paleontologists were skeptical that a single catastrophic event could have caused the mass extinction. The prevailing view at the time was that the dinosaur extinction had been gradual, a slow decline over millions of years. The idea of a sudden catastrophe, an asteroid impact, seemed too dramatic, too Hollywood, too simple. But the evidence kept accumulating. Shocked quartz, grains of quartz that show a distinctive microscopic deformation pattern called planar deformation features, produced only by the extreme pressures of a hypervelocity impact or a nuclear explosion, was found in the boundary clay. This was physical evidence of an enormous impact event. Tektites and microtektites, tiny glass spherules produced when rock is melted and ejected by an impact, were found in the boundary layer around the world. Their composition matched material from the Yucatan region of Mexico. Iridium, shocked quartz, tektites, and glass, all pointing to a massive impact. But where was the crater? In 1991, the impact site was definitively identified. The Chicxulub crater, named for a town in the Yucatan Peninsula of Mexico near its center, was discovered through geophysical surveys of the Gulf of Mexico and the Yucatan Peninsula. The crater is enormous, approximately 180 to 200 kilometers in diameter, making it one of the largest confirmed impact structures on Earth. It's buried under several kilometers of sediment and partly under the Gulf of Mexico, which is why it wasn't visible on the surface. But gravity surveys, magnetic surveys, and drilling projects revealed its structure clearly. The age of the Chicxulub impact was measured using radiometric dating techniques, specifically argon-argon dating of the impact melt rocks produced by the collision. The age came out at approximately 66.043 million years, plus or minus 43,000 years. When this age was compared with the age of the extinction event determined from biostratigraphy, the dating of geological layers from the fossils they contain, the match was within the margin of measurement uncertainty. The asteroid hit at exactly the time of the extinction. The case was closed. The impactor itself, the asteroid or comet that created Chicxulub, has been characterized by the physical evidence it left behind. Its diameter is estimated at approximately 10 to 15 kilometers, with 12 kilometers being a commonly cited central estimate. Its composition appears to have been chondritic, similar to carbonaceous chondrite meteorites, based on the geochemistry of the impact melt and the iridium enrichment. It was probably traveling at approximately 20 kilometers per second when it hit, though estimates range from 10 to 40 kilometers per second depending on the angle of approach and the original orbit. The angle of impact matters enormously for the effects. Current evidence, including the asymmetric distribution of ejecta and the pattern of shock-deformed rock around the crater, suggests the impactor struck at a relatively steep angle, approximately 45 to 60 degrees from horizontal. This angle maximized the amount of sulfur-bearing rock vaporized by the impact, with enormous consequences for the subsequent atmospheric chemistry. We'll return to that. Part 3. The first second, the impact itself. Now let's go through the event itself. In real time, second by second, then minute by minute, then hour by hour. At the moment of impact, precisely 66,043,000 years ago, give or take 43,000 years, a rock the size of a city traveling at 20 kilometers per second strikes the shallow sea covering the Yucatan Peninsula. In the first fraction of a second, the energy of the collision is so extreme that the impactor itself doesn't really hit the ground in any conventional sense. At 20 kilometers per second, the impactor is moving faster than any wave of compression can propagate through rock. The rock below the impact point cannot get out of the way. The impactor punches through the shallow sea, through several kilometers of sedimentary rock, and begins plowing into the granitic basement rock beneath. The energy involved is staggering. The kinetic energy of the Chicxulub impactor, a 12-kilometer rock traveling at 20 kilometers per second, is estimated at approximately 10^24 joules. That is equivalent to roughly 100 million nuclear weapons of the type dropped on Hiroshima, detonating simultaneously. Or approximately 10 billion times the energy released by the largest nuclear weapon ever tested, the Soviet Tsar Bomba. In the first second, the impactor penetrates deep into the crust. The rock surrounding the impact point is compressed to extraordinary pressures, millions of atmospheres. Both the impactor and a substantial volume of the surrounding rock are instantly vaporized, not melted. Vaporized, converted directly from solid rock to superheated plasma at temperatures exceeding 10,000 degrees Celsius. This vapor plume, a fireball of superheated gas and vaporized rock, begins expanding upward and outward at enormous speed. It punches through the atmosphere in seconds. Material is ejected not just upward, but in all directions, some of it at velocities exceeding escape velocity, meaning it leaves Earth's atmosphere entirely and enters orbit around Earth, or escapes into interplanetary space. In the first few seconds, the crater begins to form. The contact and compression phase gives way to the excavation phase. The outward moving pressure wave scours an enormous bowl out of the crust. Rocks that were seconds ago kilometers underground are thrown upward and outward at hundreds of kilometers per second. The crater bowl grows from nothing to 100 kilometers across in a matter of minutes. Then the rebound. When the outward excavation slows, the crater floor, which has been deeply compressed and then released, rebounds upward. The central peak of the Chicxulub crater, buried under sediment today, represents this rebound. Rock that was temporarily several kilometers underground, briefly thrust upward in a mountain that rose and collapsed in minutes. The entire excavation and rebound process, the formation of a crater 180 to 200 kilometers across, was completed in approximately 10 minutes. 10 minutes. In 10 minutes, one of the most consequential geological events in the history of life had been initiated. The physical crater was formed. The ejecta was on its way. The atmospheric plume was expanding. The consequences were beginning to propagate. Part 4. The first hour. Fire from the sky. In the first hour after impact, the most immediate threat to life was not the impact itself. It was what the impact sent into the sky. The ejecta, the material thrown out of the crater by the impact, followed ballistic trajectories. The fastest ejecta, traveling at or near escape velocity, reached orbit within minutes. Other material was thrown at high angles into the upper atmosphere. Within an hour, ejecta was raining back down across the entire planet. When a piece of rock traveling at several kilometers per second re-enters the atmosphere, it heats the air around it through compression. The air molecules can't get out of the way fast enough, and they're compressed and heated. The rock glows. This is the same process that makes meteors visible as they burn up. The rock is heated by air compression, not by friction, as is commonly believed. During the first hour after the Chicxulub impact, the global sky was filled with billions of pieces of ejecta re-entering the atmosphere simultaneously. From the perspective of an animal anywhere on Earth, the sky was not dark. It was on fire. Researchers have calculated the total energy deposited into the atmosphere by the re-entering ejecta over the first hours after the impact. The result is striking. The thermal energy deposited by the ejecta re-entry was sufficient to heat the global atmosphere significantly, perhaps by tens of degrees, within the first few hours. From the perspective of the surface, the sky would have glowed a deep red-orange, brighter than an overcast day. For hours, the infrared radiation from this glowing sky would have been sufficient to ignite vegetation on exposed surfaces globally. This is one of the most contested aspects of the impact scenario, whether the global thermal pulse was sufficient to ignite wildfires across the entire planet simultaneously. Some researchers argue that the thermal pulse was brief, and the radiated energy was insufficient to ignite moist vegetation. Others argue that even brief heating was sufficient to kill animals exposed to the sky. The evidence from the geological record, specifically the presence of charcoal in boundary layer sediments at many sites, indicating fires, supports widespread burning, though the geographic extent is still debated. What is not debated is that anything near the impact site, within hundreds or thousands of kilometers, experienced conditions beyond anything survivable. The thermal blast, the ejecta, the ground motion from seismic waves, the tsunamis from the impact on the shallow sea, all of these together created a zone of immediate total destruction around the impact site. The seismic waves generated by the impact were enormous. An earthquake of magnitude 11 or greater off the top of the existing Richter scale propagated through Earth's crust. These seismic waves caused landslides and destabilization across the entire Americas and potentially globally. They triggered additional volcanic activity at existing volcanic systems. They sent enormous tsunami waves outward from the impact site across the shallow sea that covered much of what is now the Gulf of Mexico. The Chicxulub impactor struck in relatively shallow water, perhaps 100 to 200 meters deep at the site of impact. The tsunami generated by the impact was not a simple wave. It was a complex series of waves, some generated directly by the impact and displacement of water, others generated by the seismic activity. Geological evidence, disturbed sediment layers, chaotic deposits of mixed material from different environments, indicates that tsunamis from the Chicxulub impact reached hundreds of kilometers inland across what is now the southern United States and propagated across the Atlantic Ocean. Part 5. The first day. What the atmosphere became. By the end of the first day, the immediate physical catastrophe of the impact was largely over. The ejecta had fallen back. The fires, where they had started, were burning. The tsunamis were propagating across the oceans. But the atmosphere had been fundamentally transformed. The Chicxulub impactor struck rock that was extraordinarily unfortunate in its composition. The Yucatan platform, the geological formation underlying the impact site, is composed primarily of carbonate rocks and dolom, and evaporites, bearing rocks, primarily gypsum and anhydrite. These rock types are particularly reactive when vaporized by an impact. When carbonate rocks are vaporized, they release carbon dioxide. When sulfate rocks are vaporized, they release sulfur dioxide and sulfur trioxide. The Chicxulub impact vaporized an enormous volume of these rocks. Estimates suggest tens of trillions of tons of sulfur-bearing compounds were injected into the stratosphere. In the stratosphere, sulfur dioxide reacts with water vapor to form sulfuric acid aerosols, tiny droplets of sulfuric acid suspended in the upper atmosphere. Sulfuric acid aerosols are extraordinarily effective at reflecting sunlight. They are the same aerosols that cause the dramatic cooling effect of large volcanic eruptions. The 1991 eruption of Mount Pinatubo in the Philippines injected enough sulfur into the stratosphere to cool global temperatures by about 0.5 degrees Celsius for 2 years. The Chicxulub impact injected perhaps 100 billion tons of sulfur into the stratosphere, roughly 50,000 times more than Pinatubo. The resulting sulfuric acid aerosol layer would have been far thicker, far more effective at blocking sunlight, and far more persistent than anything produced by any volcanic eruption in recorded history. The cooling effect of this aerosol layer has been calculated by climate models. Global temperatures may have dropped by 10 to 20 degrees Celsius within weeks of the impact. From a world that was already warmer than today, temperatures plummeted toward freezing at many latitudes. The tropics, which had been warm and humid, became cold. The already cold high latitudes became far colder. And it wasn't just cooling. The sulfuric acid aerosols, when they eventually precipitated out of the atmosphere, became sulfuric acid rain. The acidity of rainfall globally increased dramatically. This acid rain killed vegetation that had survived the initial impact event. It acidified rivers, lakes, and the surface layers of the ocean. The carbon dioxide released by the vaporization of carbonate rocks contributed a greenhouse warming effect, but this would not be felt immediately. In the short term, the sulfate aerosols dominated, cooling the planet. The long-term warming effect of the CO would only emerge over decades and centuries as the aerosols gradually settled out of the stratosphere. But the sulfate aerosols were not the only thing injected into the atmosphere. The fires that burned in the hours after the impact produced soot, fine carbon particles that are also highly effective at blocking sunlight. Some models suggest that the soot from impact triggered wildfires contributed significantly to the global darkness. Others suggest that soot was less important than sulfate aerosols. The relative contributions of soot versus sulfate aerosols to the post-impact darkness is still an area of active research. What is not in dispute is the result. Within days of the impact, sunlight reaching the Earth's surface had been reduced to a tiny fraction of normal. Within weeks, it may have dropped to near zero in some models, a level comparable to a moonlit night, insufficient for any photosynthesis. The lights went out on the surface of the entire planet. Part 6. The months and years after. Impact winter and the collapse of food chains. What happened when the sunlight disappeared? Plants need sunlight for photosynthesis. Without photosynthesis, plants cannot produce the sugars that fuel their growth. Without growth, plants die. The timing of the impact, whether it was spring, summer, fall, or winter in the northern hemisphere when the asteroid struck, affected which plants were in which stage of their life cycle. But regardless of season, months of near total darkness would be fatal to most vegetation. The models of post-impact darkness suggest that photosynthesis was reduced to near zero across much of the planet for a period of at least months. Some models suggest years. The duration of darkness depended on the total mass of light-blocking aerosols and soot, and on how quickly they settled out of the atmosphere. Particles of different sizes settle at different rates. The finest particles can remain in the stratosphere for years. Without photosynthesis, the base of the food chain collapsed. The consequences cascaded upward through the ecological hierarchy with terrible efficiency. Herbivores, animals that eat plants, starved. Not all immediately. Some could survive for weeks or months on seeds, tubers, or other stored plant material. But with new plant growth suppressed, the herbivore population began to decline rapidly. Smaller herbivores, insects, small mammals, lizards, faced immediate pressure. Larger herbivores, the great sauropods, the hadrosaurs, the ceratopsids, were particularly vulnerable because of their size. A large herbivore needs an enormous amount of vegetation every day. When vegetation stops growing and existing vegetation dies, a large herbivore has a limited time before it starves. The large dinosaurian herbivores, Triceratops, Edmontosaurus, Ankylosaurus, the Titanosaurs, were among the most vulnerable animals on Earth in the months after the impact. Their size, which had been an advantage in a world of abundant vegetation, became a liability in a world where food was disappearing. And when the herbivores died, the carnivores followed. An apex predator like Tyrannosaurus rex was eating large herbivores, hadrosaurs and ceratopsids, as its primary prey. When those prey animals disappeared, T-Rex had nothing to eat. The top predators were the last to die, but they died. The collapse of the terrestrial food chain was not instantaneous. It played out over months to years, a slow starvation cascading through every level of the ecosystem. What the geological record shows is not a gradual decline, but a sudden cutoff. Species that were abundant in the last Cretaceous sediments simply do not appear in the earliest Paleocene sediments above the boundary layer. The marine environment fared no better. The base of marine food chains is phytoplankton, microscopic photosynthetic organisms floating in the surface waters of the ocean. Without sunlight, phytoplankton died. Without phytoplankton, the zooplankton that fed on them died. Without zooplankton, the small fish that fed on them died. The collapse propagated up the marine food chain, just as it did on land. The ammonites, those coiled shell marine predators that had been a feature of the oceans for hundreds of millions of years, went extinct. Mosasaurs, large marine reptiles, went extinct. Plesiosaurs, long-necked marine reptiles, went extinct. Many lineages of fish were severely reduced. The marine extinction was as complete as the terrestrial extinction, and it operated through the same mechanism: the collapse of photosynthesis at the base of the food chain. Part 7. The Acid Oceans. The second catastrophe in the sea. There was a second, independent catastrophe happening in the oceans simultaneously. The Chicxulub impact vaporized carbonate rock and injected enormous quantities of carbon dioxide into the atmosphere. This CO, when it dissolves in seawater, forms carbonic acid. The acidification of the ocean surface, ocean acidification, was rapid and severe. Ocean acidification is particularly devastating to organisms that build shells or skeletons out of calcium carbonate, calcite, or aragonite. These include ammonites, many types of marine plankton, corals, and numerous other marine invertebrates. When seawater becomes more acidic, calcium carbonate dissolves. Shells thin. Skeletons weaken. At high enough acidity, organisms cannot maintain their calcium carbonate structures at all. The impact acidification event was far more severe than anything the modern ocean has experienced. Models suggest ocean surface pH dropped by perhaps 0.5 to 1 pH unit in the years following the impact, a change that would have been catastrophic for calcifying organisms. The planktonic foraminifera, microscopic single-celled organisms that build tiny calcium carbonate shells and are among the most important components of the open ocean food web, were particularly devastated. Before the impact, foraminifera were extraordinarily diverse and abundant. Hundreds of species lived in the Cretaceous Ocean. After the impact, the diversity collapsed to just a handful of species. The recovery took millions of years. The combined effect of the food chain collapse from darkness and the direct chemical destruction of calcifying organisms produced a marine extinction of staggering scale. Approximately 75% of marine species went extinct at the Cretaceous-Paleocene boundary. The ocean ecosystem that had developed and diversified over hundreds of millions of years was effectively reset to a near bare minimum of surviving lineages. And yet the ocean recovery, when it eventually came, was relatively rapid by geological standards. Within a few million years, the oceans were refilled with new lineages of organisms. Life is resilient. But the specific organisms that had filled the Cretaceous Ocean, the ammonites, the mosasaurs, the plesiosaurs, the specific planktonic communities, were gone forever. Part 8. The Deccan Traps, the catastrophe that was already happening. Now we come to the aspect of the dinosaur extinction story that most popular accounts ignore completely. The asteroid did not strike a healthy planet. It struck a planet already in the middle of a prolonged volcanic crisis. The Deccan Traps are one of the largest volcanic features on Earth, a vast plateau of flood basalt covering approximately 500,000 square kilometers of what is now the Deccan region of India, with lava flows kilometers thick. They were produced by one of the most intense episodes of volcanic activity in the last 100 million years. A large igneous province event in which enormous volumes of basaltic lava poured out of fissures in the crust over a period of roughly 750,000 years, straddling the end of the Cretaceous period. The Deccan Traps eruptions began approximately 400,000 years before the Chicxulub impact and continued for approximately 300 to 500,000 years afterward. This means that for the entire final period of the Cretaceous, the atmosphere was being loaded with volcanic gases from the Deccan traps. Flood basalt eruptions of this scale emit enormous quantities of carbon dioxide, sulfur dioxide, hydrogen fluoride, and other gases over their lifetime. The total CO released by the Deccan traps over its eruptive lifetime was sufficient to warm global temperatures by perhaps 2 degrees Celsius. The sulfur dioxide emissions produced short-term cooling events, volcanic winters lasting years to decades, punctuating the longer-term warming trend. The combination of volcanic CO warming and volcanic SO cooling produced a climate that was increasingly unstable in the last 400,000 years of the Cretaceous. There is evidence in the fossil record of stress on dinosaur ecosystems, reduced diversity in some lineages, changes in vegetation. In the final 100,000 to 200,000 years before the impact, the Deccan traps may have already been pushing the biosphere toward increased vulnerability. And then, 66 million years ago, the asteroid hit. The relationship between the Chicxulub impact and the Deccan traps eruptions turns out to be even more intimate than just their coincidental timing. There is evidence, still debated but increasingly supported by data, that the seismic waves from the Chicxulub impact may have intensified the Deccan traps eruptions. The impact of a 12-kilometer asteroid created seismic waves equivalent to a magnitude 11 earthquake propagating through the entire Earth. These seismic waves would have passed through the magma chambers feeding the Deccan traps, magma systems that were already under pressure and primed to erupt. There is geological evidence that the rate of Deccan eruptions increased significantly after the impact. Some analyses show a 2- to 3-fold increase in eruption rate in the period immediately following the impact, based on the thickness and accumulation rate of lava flows. If this is correct, and the evidence is suggestive but not yet definitive, then the Chicxulub impact didn't just cause its own catastrophic effects. It also triggered an intensification of the Deccan traps eruptions, adding another layer of volcanic gases and instability to an atmosphere and ecosystem already struggling with the direct impact effects. This makes the Chicxulub impact even more consequential than the simple rock hits Earth and everything dies narrative suggests. The impact may have hit a planetary system that was already under stress and then actively made that stress worse. Part 9. Who survived? A&D-Y. The extinction was not total. Life survived. Approximately 25% of species made it through. And understanding who survived and why tells us as much about the extinction as understanding who died. The most important pattern in the survival data is size. On land, virtually nothing with a body mass greater than 25 kilograms survived in the northern hemisphere. The large dinosaurs, all of them, went extinct. Large marine reptiles, mosasaurs, plesiosaurs, went extinct. Large pterosaurs went extinct. But small animals, small mammals, lizards, snakes, small birds, insects, frogs, salamanders survived at much higher rates. Why does size matter so much? 2 reasons, both related to the food chain collapse. First, small animals need less food than large animals. A small mammal weighing 50 grams might need just a few grams of food per day. Insects, seeds, fungi, dead organic matter. A large herbivorous dinosaur might need hundreds of kilograms of vegetation per day. When the plant food supply collapses, small animals can survive on scraps and alternative food sources, detritus, dead organic matter, insects that large animals cannot exploit efficiently. Second, small animals have faster metabolisms and faster reproduction rates. They can potentially recover population numbers quickly after a catastrophe. Large animals with long gestation periods and small litter sizes recover far more slowly. The mammals that survived the end Cretaceous extinction were small, mostly mouse to rat-sized. They were generalists, able to eat a variety of foods including insects, seeds, fungi, and carrion. Many were at least partially fossorial, able to dig burrows and retreat underground, away from the worst of the atmospheric effects. And crucially, they happened to be in the right places where some food remained available when the catastrophe struck. Birds, which are technically avian dinosaurs, also survived. But not all birds. The large ornithuromorph birds went extinct. The birds that survived were the ancestors of modern birds, smaller, more generalized forms that could exploit the collapsed food web more effectively. In the oceans, the pattern was similar. Small organisms with short generation times and flexible diets survived better than large organisms with specific diets. The organisms that recovered the fastest, and that would eventually give rise to the diverse modern marine fauna, were those that could survive on whatever organic matter remained available in a devastated ocean ecosystem. Crocodilians survived. These semi-aquatic animals could exploit both aquatic and terrestrial food sources and could survive on very little food for extended periods. A crocodile can go months without eating if necessary. Turtles survived for similar reasons. Lizards and snakes survived. The ancestor of all modern squamates made it through the extinction. The selectivity of the extinction is one of its most important features. It was not random. It had structure. Size mattered. Diet mattered. Metabolic rate mattered. Geographic location mattered. The extinction did not simply kill everything indiscriminately. It killed according to specific vulnerabilities, and in doing so, it reshuffled the deck of life, eliminating the dominant groups and opening ecological space for the survivors. Part 10. The mammals inherit the earth, the aftermath. In the immediate aftermath of the extinction, in the first thousands of years of the Paleocene, the world looked like a wasteland. The fossil record from this interval shows impoverished ecosystems, few species, low diversity, small body sizes, simplified food webs. It's been called the fern spike interval because the first plants to recover in many regions were ferns, opportunistic colonizers that can grow quickly in disturbed soil. But recovery was already beginning. The mammals that had survived the extinction began to diversify. In the absence of the large dinosaurs that had occupied every large animal ecological niche for 165 million years, those niches were suddenly open, empty, available. The evolutionary response was explosive. Within approximately 10 million years of the extinction, in geological terms, almost instantaneous, mammals had diversified from small, generalized insectivores and omnivores into an enormous range of body sizes and ecological roles. Large herbivores evolved to fill the niches left by hadrosaurs and sauropods. Large carnivores evolved to hunt them. Aquatic mammals evolved to fill niches left by mosasaurs and plesiosaurs. Bats evolved, the only mammals to achieve true powered flight. Primates diversified. The pace of mammalian diversification after the extinction has been studied in detail using phylogenetics, the statistical analysis of evolutionary relationships based on DNA and fossil evidence. The results are striking. Mammalian body size diversification accelerated dramatically in the first few million years after the extinction, with lineages rapidly evolving toward larger body sizes as ecological opportunities opened up. The key point is this: the extinction of the non-avian dinosaurs did not simply remove a group of animals. It removed the ecological structure that had constrained mammalian evolution for 165 million years. For all that time, mammals had been restricted to small body sizes by the ecological dominance of dinosaurs. Every attempt by a mammalian lineage to evolve into the large animal niches was blocked by the dinosaurs that already occupied them. The Chicxulub impact removed those blocks. The mammals, which had been waiting in the ecological wings for 165 million years, finally had their chance. And they took it. Within 25 million years of the extinction, mammals included animals as large as Paraceratherium, an enormous hornless rhinoceros relative that may have been the largest land mammal ever, weighing perhaps 15 to 20 tons. Within 30 million years, whales had evolved from land-dwelling ancestors and were filling the open ocean niches left by the marine reptiles. Within 40 million years, the primate lineage had diversified into the ancestors of monkeys, apes, and eventually, 66 million years after the asteroid hit humans. We exist because the asteroid hit, not in a poetic sense, in a direct causal biological sense. The asteroid hit, the dinosaurs died, the mammals diversified, the primates evolved, and eventually one lineage of primate developed language and technology and the capacity to look back at the geological record and reconstruct the event that made us possible. That's the full circle of the story. We are the children of the catastrophe. Part 11. How Science Figured It Out. 50 Years of Evidence. The story of how we pieced together the extinction mechanism is as interesting as the mechanism itself, because it didn't happen all at once. It happened incrementally, over 50 years, as new technologies and new approaches opened new windows into the geological record. The Alvarez iridium discovery in 1980 was the beginning, not the end, of the scientific story. The identification of iridium at the boundary layer was a crucial clue, but it didn't immediately convince everyone. Skeptics raised objections. Perhaps the iridium came from sustained volcanic activity rather than a single impact. Perhaps the extinction was gradual rather than sudden. Perhaps the boundary layer represented a gap in the sedimentary record rather than an instantaneous event. Each objection required evidence to address. The discovery of shocked quartz addressed the volcanic alternative. Volcanic eruptions don't produce the characteristic planar deformation features in quartz grains that hypervelocity impact does. The discovery of the Chicxulub crater in 1991 provided the physical impact site. The precise radiometric dating of both the impact and the extinction, showing that they occurred at the same time within measurement uncertainty, addressed the timing question. The question of whether the extinction was sudden or gradual required statistical analysis of the fossil record, counting species in sediment layers above and below the boundary and determining whether the decline was rapid or slow. This work, carried out across multiple fossil sites on multiple continents, consistently showed that the decline was abrupt, occurring within the time resolution of the geological record, which at that boundary is typically tens of thousands to hundreds of thousands of years. Understanding the kill mechanisms required modeling, climate models to simulate the atmospheric effects of the impact aerosols, ocean chemistry models to simulate acidification, ecological models to simulate food chain collapse. These models became more sophisticated as computing power increased. The early models of the 1980s and 1990s gave rough estimates of global cooling. The models of the 2000s and 2010s incorporated more detailed aerosol physics, more realistic land surface and ocean interactions, and more sophisticated representations of ecosystem dynamics. The contribution of the Deccan traps to the extinction was recognized early. The massive flood basalts had been dated to the end Cretaceous period for decades. But the question of whether the Deccan traps were a significant contributor to the extinction, or merely a coincidental contemporaneous event, required detailed isotopic analysis of the lava flows to establish precise timing. The work of multiple research teams over the past 2 decades has clarified that the Deccan traps eruptions were already stressing the biosphere before the impact, and that the eruption rate increased after the impact, potentially complicating and prolonging the recovery. The question of what exactly killed the animals, whether it was the darkness, the cold, the acid rain, the direct heat, the food chain collapse, or some combination, required analysis of the fossil record at multiple sites, combined with the climate and ecological modeling. Different researchers have emphasized different kill mechanisms, and there is still active debate about their relative importance. What has emerged from 50 years of work is not a simple story. It's a complex, multi-causal narrative in which multiple catastrophic processes operated simultaneously and interactively, with a specific combination of impactor composition, target rock composition, impact angle, pre-existing volcanic stress, and ecological structure all contributing to the severity and specificity of the extinction. The science is not finished. New drilling projects at the Chicxulub crater continue to recover impact melt rocks and drill through the boundary layer, providing new data on the sequence of events. New fossil sites are discovered that provide new information about the diversity and distribution of species in the last Cretaceous. New geochemical analyses provide new constraints on the atmospheric chemistry of the impact aftermath. New phylogenetic analyses refine the evolutionary timing of the mammalian diversification. We know vastly more than we did when the Alvarez team published their iridium discovery in 1980. We will know more still in 2080. Part 12, What Wasn't an Asteroid? Ruling out other explanations. The asteroid impact hypothesis is now firmly established as the primary cause of the Cretaceous-Paleocene extinction, but science requires ruling out alternatives, and the history of the field includes serious consideration of other explanations that had to be systematically eliminated.
The most prominent alternative was the volcanic hypothesis. The idea that the Deccan traps eruptions alone without any asteroid caused the extinction. This hypothesis was championed by some scientists in the 1980s and 1990s who were skeptical of the impact hypothesis. They argued that the iridium enrichment could have come from volcanic degassing, that the extinction was gradual rather than sudden, as the volcanic hypothesis would predict, and that the physical effects of the Deccan eruptions were sufficient to explain the extinction.
The volcanic hypothesis has been progressively weakened by the evidence. The shocked quartz cannot be produced by volcanism. The global distribution of tektites points specifically to a large impact event. The precise coincidence of the impact age and the extinction age, confirmed by multiple independent dating methods at multiple sites, is difficult to explain as a coincidence. The pattern of extinction, sudden, global, affecting marine and terrestrial ecosystems simultaneously, is more consistent with an acute global catastrophe than with prolonged volcanic stress. The current consensus is that the Deccan traps contributed to environmental stress before and after the impact, but that the Chicxulub impact was the primary driver of the extinction. The eruptions are real, significant, and relevant, but they are not sufficient to explain the extinction on their own, and the timing of the extinction is too precisely coincident with the impact to be explained by volcanism alone. Another alternative that was briefly considered and quickly eliminated was climate change from continental drift. The positions of the continents affect climate through their influence on ocean circulation, albedo, and the distribution of land and sea. In the late Cretaceous, continental drift was producing climate changes, but these were far too slow to produce a sudden global extinction. Continental drift operates on timescales of millions of years. The extinction happened in thousands to tens of thousands. Disease, predation pressure, and other biological hypotheses for the dinosaur extinction were also considered and ruled out. Diseases don't cause globally simultaneous extinction across multiple taxonomic groups and both marine and terrestrial environments. Predation pressure by mammals, sometimes invoked in early popular accounts of the dinosaur extinction, fails because mammals were too small and too rare to significantly impact dinosaur populations. The convergence of evidence on the impact hypothesis, from geochemistry, from stratigraphy, from paleontology, from physics, from planetary science, is one of the strongest cases for any historical event in the geological record. It's not perfect. No scientific case ever is. But the multiple independent lines of evidence pointing to the same conclusion make it one of the most robustly supported events in Earth history. Part 13. The Lessons. What the dinosaur extinction tells us. The Chicxulub impact and its consequences are not just history. They are a lesson. And the lesson has multiple levels. The first level is about the fragility of dominant groups. The dinosaurs had dominated terrestrial ecosystems for 165 million years. They were the most successful group of large land animals in the history of the planet. And they were eliminated. Not by competition, not by climate change, not by disease, not by the mammals they had been living alongside for 165 million years, but by a single event of astronomical origin. The dominance of the dinosaurs, which must have seemed permanent, unchallengeable, was contingent on nothing striking Earth from space. Our own dominance, the dominance of large-brained, technologically capable primates, is similarly contingent. We have existed for 300,000 years. The dinosaurs existed for 165 million. If the dinosaurs' tenure could be ended in minutes by a rock from space, what does that say about the permanence of our own? The second level is about the nature of catastrophe. The Chicxulub event was not a simple, single blow. It was a cascade. Impact, then ejecta re-entry, then fire, then acid rain, then darkness, then cold, then food chain collapse, then ocean acidification, all operating simultaneously and interactively. No single element of this cascade was necessarily sufficient to cause a mass extinction alone. The total effect was greater than the sum of the parts because each element made the others more severe. This is how catastrophes work in complex systems. They cascade. They interact. They create conditions that make other negative effects more severe. Understanding the Chicxulub cascade is a template for understanding how other planetary-scale catastrophes might unfold. The third level is about the role of contingency in evolution. The mammals that survived the extinction were not the most intelligent, the most advanced, or the most capable of all the organisms alive 66 million years ago. They were small, generalized, and by most measures unremarkable compared to the large dinosaurs that dominated the Cretaceous world. They survived because their small size and dietary flexibility made them less vulnerable to the specific sequence of catastrophes that followed the impact. Evolution is not directed toward complexity or intelligence. It selects for whatever works in the current environment. The survivors of the Chicxulub extinction were the ones that happened to have traits: small size, broad diet, burrowing behavior that were advantageous in the specific conditions of the aftermath. If the impactor had been smaller, or had struck at a different angle, or had hit a different type of rock, the kill mechanisms would have been different, and the survivors would have been different. Different survivors means a different trajectory of evolution. Different evolutionary trajectory means no primates, no apes, no humans. The fourth level is about the hazard we face today. The asteroid that struck 66 million years ago was not unique. The solar system contains millions of objects, asteroids and comets, in orbits that cross Earth's path. Most are small, most will never approach Earth closely, and most that do will miss. But statistically, over geological time, large impacts are inevitable. The Chicxulub impactor was not a one in the history of the universe event. It was one of many large impacts in Earth's history, occurring at intervals determined by the population of potential impactors and the gravitational dynamics that can send them toward Earth. We now have programs, planetary defense initiatives, that monitor the population of near-Earth objects and assess the risk of future impacts. We have concepts for deflecting hazardous asteroids. The NASA DART mission in 2022 successfully changed the orbit of a small asteroid by deliberately crashing a spacecraft into it. A proof of concept for planetary defense. We are, for the first time in Earth's history, a species capable of detecting an incoming impactor and potentially preventing the kind of catastrophe that ended the Cretaceous. That capability is not a guarantee of safety. It requires sustained investment, sustained attention, and sufficient warning time. A large impactor with short warning time could still be catastrophic, regardless of our technology. But the fact that we can detect, track, and potentially deflect asteroids means that we are not as defenseless as the dinosaurs were. Part 14, The World That Emerged. Why we should be grateful for the catastrophe. This is perhaps the most uncomfortable part of the story. Because the Chicxulub impact, The event that killed 75% of Earth's species, that ended 165 million years of dinosaur dominance, that caused one of the most severe mass extinctions in the history of life, is also the event that made us possible. Not in a vague, philosophical sense. In a direct, biological, evolutionary sense. For 165 million years, mammals lived in the shadow of the dinosaurs. They were present throughout the Mesozoic era. In fact, the first true mammals evolved from therapsid ancestors at roughly the same time as the first dinosaurs, in the late Triassic period approximately 225 million years ago. Mammals and dinosaurs evolved simultaneously, lived simultaneously, competed for resources simultaneously, but the dinosaurs won. The ecological dominance of dinosaurs, their diversity, their adaptations, their range of body sizes from chicken size to the largest land animals ever, effectively excluded mammals from the large body size ecological niches. Throughout the Jurassic and Cretaceous, while dinosaurs diversified into dozens of ecological roles and reached sizes ranging from a few kilograms to 70 tons, mammals remained small. The largest Mesozoic mammals were roughly the size of a large cat or small dog. Most were mouse to rat-sized. Why? Because any mammalian lineage that began evolving toward larger size would encounter increasing competition from the incumbent dinosaurs that already filled those niches. Dinosaurs had been occupying large animal niches for tens of millions of years by the time any particular mammalian lineage might try to move into them. The incumbents had advantages, evolved behaviors, physiological adaptations, established ecological relationships that made displacement difficult. This is a well-documented pattern in evolutionary biology: incumbent advantage. The animals already in an ecological niche have advantages over would be competitors trying to enter from outside. Incumbency can maintain ecological stability for extremely long periods, far longer than the competitive ability of the incumbents alone would suggest. Because newcomers have to compete not just with the incumbents, but with the entire established ecological community built around them. The Chicxulub impact eliminated the incumbency of the dinosaurs, not gradually, through competitive displacement over millions of years. Instantaneously, in the geological sense, through the brutal, indiscriminate mechanism of global environmental catastrophe. When the dust settled, literally and figuratively, the large animal niches were empty. The mammals that had survived were still small, still generalized. But the ecological space was open. The incumbents were gone. And without incumbents to block them, mammalian evolution could finally explore the large animal body size space. The result was an evolutionary explosion of mammalian diversity that produced, over the next 66 million years, every mammal alive today. Whales and bats and elephants and horses and primates and us. All of it, the entire magnificent diversity of modern mammalian life, is the direct biological consequence of the Chicxulub impact clearing the ecological stage. We are the beneficiaries of a catastrophe. The same event that killed 3/4 of Earth's species created the conditions for our eventual existence. This is not a comfortable thought. It forces a kind of moral accounting that doesn't resolve cleanly. The extinction of the dinosaurs was not a good thing in any simple sense. It was a catastrophe of almost unimaginable scale, a tragedy for the extraordinary diversity of Cretaceous life. But it is our origin. And knowing that it is our origin, knowing the specific mechanism that opened the ecological space that mammals filled, knowing the specific chain of causation that led from an asteroid in space to the emergence of intelligence on Earth, changes how we understand ourselves and our place in the history of life. Part 15. The question underneath everything. There's a question that underlies everything we've discussed tonight, and it's worth stating explicitly. We exist because an asteroid happened to strike Earth 66 million years ago. Not because it was inevitable. Not because some force guided it toward Earth at the right moment. Not because the universe was arranged to produce beings capable of asking questions about it. But because an asteroid happened to be in a particular orbit, happened to be perturbed by some gravitational interaction, happened to cross Earth's path at a particular moment, and happened to strike at a particular location with a particular composition of target rock that maximized the sulfur. Aerosol loading of the atmosphere. Chance. Contingency, the specific, unrepeatable particularity of events that could have gone differently. If the impactor had been smaller, the extinction might have been less severe. The dinosaurs might have survived. Mammals might still be small and insignificant. If the impactor had been larger, the extinction might have been so severe that even the small mammals didn't survive, and the recovery might have been led by some other group entirely. If the target rock had been different, if the impactor had struck granitic basement rock rather than sulfate-rich carbonate rock, the sulfate aerosol loading would have been less severe. The darkness would have been shorter, the extinction less complete. Everything is contingent. Everything could have been different. The specific path that led to us required a specific sequence of events, each of which was not guaranteed, and many of which involved the specific, unrepeatable details of particular moments in geological time. This is humbling. It means that the universe did not inevitably produce us. We are not the culmination of a directed process. We are one outcome among the vast space of possible outcomes. The outcome that happened to be selected by the specific sequence of events on this specific planet over the last 4.5 billion years. But there's another way to look at it. The contingency that makes our existence seem improbable also makes it remarkable. We are here, despite the long odds. We are here, and we are capable of understanding the events that made us possible. We can read the thin layer of iridium-rich clay at the boundary between the Cretaceous and the Paleocene and know what it represents. We can drill into the buried Chicxulub crater and measure the ages of the impact melt rocks. We can reconstruct the sequence of events that followed the impact, the fire, the darkness, the cold, the collapse of food chains. From the chemical and physical signatures preserved in the rock, we can know our own origin. We can trace the chain of causation from an asteroid in space to intelligence on Earth. And we can look at that chain, 66 million years of it, from catastrophe to consciousness, and recognize it as the story of how we came to exist. That's something the dinosaurs couldn't do. They couldn't understand the asteroid that was coming. They couldn't read the sky and know what it meant. They couldn't trace the long history that had led to them, or project forward to what might come after. We can. That capacity for understanding, for tracing causes and consequences through deep time, is itself the product of the chain of events that began with the asteroid. The universe produced, through an improbable sequence of contingent events, something that can understand the universe. That's worth thinking about. Epilogue. The thin layer of clay. In rock outcrops around the world, in Spain, in Italy, in Denmark, in New Zealand, in the American West, in the bottom of ocean drill cores, there is a thin layer of clay, sometimes less than a centimeter thick, sometimes slightly more. A dark reddish-brown band of rock that separates the limestone and chalk of the Cretaceous from the clay and mudstone of the Paleocene. Below that layer, dinosaurs, ammonites, mosasaurs, a world that had been developing for 165 million years. Above that layer, none of those things. A world reset, impoverished, beginning again. In that thin layer, in the iridium enrichment, in the shocked quartz grains, in the microscopic glass spherules, in the soot and the charcoal, is preserved the record of one of the most consequential moments in the history of life on Earth. A moment that lasted seconds, whose effects played out over years and decades and millennia, and whose evolutionary consequences are still unfolding 66 million years later, in the form of every mammal alive today, including you. The clay layer is not dramatic to look at. It doesn't glow. It doesn't move. It sits in the rock, a centimeter of compressed time, waiting to be read by those who know how. We know how now. It took 50 years of science, of geochemistry and paleontology and climate modeling and planetary physics and statistics and drilling and dating and argument and revision to learn how to read it. But we can read it. We can hold a sample of that clay in our hand and know, from its chemistry, that 66 million years ago an asteroid 12 kilometers wide struck the Earth at 20 kilometers per second and ended 165 million years of dinosaur dominance and opened the ecological space that eventually produced us. We can know that. The dinosaurs didn't know what hit them. We do. And knowing it, understanding the mechanism, understanding the scale, understanding the contingency of our own existence on that specific impact at that specific time, is one of the most extraordinary things that the product of that impact has ever done. Sleep well tonight. On a planet that has survived catastrophes you can barely imagine, that has reset itself, recovered itself, rebuilt itself from near total destruction more than once, that has produced, from the survivors of each catastrophe, new forms of life more diverse and more complex than what came before. The asteroid killed the dinosaurs, and in doing so, it set in motion the sequence of events that produced everything alive on Earth today, including the mind that can look back across 66 million years and understand what happened. That's the final gift of the catastrophe.